Welcome back, and in this video series we're going to have a look at Chapter 2, and in Chapter 2 we're going to be focusing on computers and the machines behind computing. So we're going to focus fairly closely on the following learning objectives, which is defining computer systems, describing all the different components that are going to be required. These are things that you're going to need to know in your day-to-day work. You may know a lot of these. This will give you an opportunity to find out what the latest stuff that's out there on the market at the time of this recording, and then discuss the history of computer hardware. And I think it's important that you understand where it was and where we're at and where we're going. Explain the factors distinguishing the computer power of computers. So how does all the computer powers and the terminology, summarize computer operations. We'll discuss a little bit of the input, output, and memory devices, and look at the hardware components, and explain how computers are classified, describing the two major types of computers, and finally finishing off with a list and generating a computer language. List of generating computer languages. What kind of computer languages are out there? So this graphic kind of sums up what we're going to be looking at in this, and it's you'll probably recognize a lot of this, but you should be familiar with all the terminology. All right, so a computer is a machine, and what does it do? What's its primary focus? Well, it's designed primarily to accept data or collect input, and once we've collected input, we're going to take that input and we're going to process it in some way, and we're going to do that using human intervention. And then finally, we're going to output information. If you think back to Chapter 1, when we're looking at MIS and the bigger picture, we looked at data is stored in a database, and then database is then process becomes information. And so MIS is very closely connected to the hardware, because the hardware is designed specifically to collect data or input and then process it or do the calculations and then output it into meaningful reports and information. So a lot of times you'll hear people saying a computer is an input-output device or input process output. You'll hear those from time to time. So to accomplish this, you're going to need to have a software program or instructions. And we do that in the way of computer programs. And what is a computer program? It's simply just a step-by-step kind of instructions to perform some task that you're trying to do. And so computer programmers, they'll be given a task of what some user wants to accomplish, and they'll write out an algorithm or a step-by-step direction of how to perform that in a variety of languages. Now these languages are not English or another language that we communicate as humans. These are languages that are specifically designed for computers to interpret it. Now, even though the computer language is written in English terms, you need to use a computer type of language and logic to write this, and it's very specific, and the grammar, you might say, or they call it the syntax, has to be very precise for the computer to be able to interpret it, process it, and then eventually output the results. So there's a term I used in Chapter 1 called GEGO, and I said it was garbage in is garbage out. You'll hear this term a lot when talking about managing information systems, because whenever you're trying to manage a system and the input going into the computer is erroneous or garbage, the information that it can process is going to be garbage. So, I mean, a quick example would be if you just wanted to calculate 3F times 3 pound or ampersand sign, you're going to get an error because the information going in makes no sense. It's erroneous, and the output you're going to get is erroneous. So it's garbage in, garbage out. Now, writing a computer program, first we got to identify what needs to be done, and then plan a method to achieve this goal by writing out some pseudocode or sort of planning out this algorithm that you would like the computer program to do. Select the right computer language that best suits the environment that you're going to be developing it in. So selecting the right language really pertains to if you're going to be developing, let's say, a mobile app. You might use a particular language compared to if you're going to do a database collection. You might use a different type of language for something like that. So it really depends on the problem that you're trying to solve on how you select the computer language. the program language that you're actually typing into the computer, it's not referred to as like the grammar. It's when you type in the code in, it's referred to as syntax, or the source. Syntax is how you correctly type out code. It's referred to as the source code. So computers don't read letters like we do. They read and store and interpret and process using a binary system, which is like turning circuits on and off. And at first, I think what students hear with binary, just turning circuits off and on, is very confusing. And I'll get into this a little bit further of how the computer can make sense of a binary number system. We usually, when we talk about number systems, a lot of we talk usually in decimal systems in a base 10, but computers do it in base 2, which is the binary. They do an octa language or numbering system, which is base 8, and then there's other ones as well. But at the root level, the source code has to be translated into a binary code, and it's basically just ones and zeros. Now, there's different components within a computer system. So the hardware components, that's anything you can physically touch would be identified as the computer components. So these physical devices, such as like you touch the keyboard, of course, the monitor. Now it says the processing unit, or the central processing unit, which I'll get into here in a moment, which is the chip, and other things that you might have in there as well, like a printer. You might have other peripheral devices. Anything that you can touch would be considered a hardware component. Software components is the programming language that we just talked about. So this is the programs written by the computer programmer in a particular computer language. And these languages would be something like Microsoft's C#. It might be something like Java or Python, or there's a variety of different programming languages out there. And each language has its own affordances, its own characteristics that allow the developer, the programmer, to write a program in a very specific way to solve a particular problem. Now, even though these problems can be solved using the same language, sometimes these languages are better than others to do certain type of tasks. And there's lots and lots of other programming languages out there. Now, I just mentioned the central processing unit. That's the brain chip in the computer. You might have heard of Intel. You might have heard the i3, the i5, the i7, and so on. These are the central processing chips that your computer has inside. And this is really where everything ends up going to central. It gets processed and then redistributed to wherever it happens to be. And within the CPU, one of its key functionalities is to perform logical calculations in this arithmetic logical unit, or ALU. It performs these calculations using, like, when you're adding, subtracting, multiplying, dividing, like a calculator. It also does things like comparison analysis when you're comparing it using relational operators, like it's less than, greater than, or it's equal to. So if you phrase the question like, if somebody comes and wants to do a comparison, they can use these comparison operators. All right, the control units and the central control unit really helps, like, the director of where information should be directed to, and where should it be stored, and where should it be outputted, where is it being collected from. So the central unit, that central processing unit, is really broken down into two parts: this logical unit and the control unit. So the control unit directs and moves the information to where it's supposed to be sent to. So you probably have opened a computer, have seen this type of thing before, where there's a main chip. You can see where all of these lines are coming into the chip. They refer to this as the bus. And the data flows into the chip, it gets processed, and then gets redistributed or calculated inside here. So inside here, there's that arithmetic unit, the ALU, and there's also the central processing unit that does the processing in there as well. So computers can either have a single processor or multiprocessors, and it just means that the more processors, the more you can calculate, the faster you can output this information, and really depending on the tasks that you're doing. So you can have multiprocessors. Now, today, there's a lot of computers that have multiprocessors in them. So thinking about this in an input, process, output, back to the earlier slide, when you're typing on the keyboard, you're inputting some information or instructions that goes into the computer, and then whether you need to calculate something or control that information, the central processing unit is responsible for redirecting the information either to store it in a memory internal memory or hard drive or a volatile memory like RAM, we'll get into a second, or output the information as a report or some kind of information that we've calculated. Now, I just mentioned a bus, and the term bus really refers to the number of channels that a computer can channel in data and bring it into to the motherboard from the CPU to the memory. So these larger buses allow the transfer of data into the system at a higher rate. Because it's got a larger bus, it can accept all that input at a much quicker rate. And there's all sorts of different types of buses. They used to start off with an 8-bit bus, and then it went to a 16-bit bus. And I'm not sure what the current ones are right now. But when they're talking about buses, they're talking about the data flowing in. And it can be flowing in either as parallel or serial. Parallel means that the data is flowing in through multiple lines going in. And then a serial means that there's only one going in at a time. You may recognize serial from the USB port, Universal Serial Bus, which is the data is going into the through a USB port, one kind of 0 and 1 at a time. So it turns switches on and off one at a time. So with a parallel port, you'd have a whole group of these all going through at the same time. So it's a lot faster to have a parallel input and output than it would be for a serial. Now, with today's computers and universal serial buses or USB, like when you guys plug in your USB, you're really talking about a bus because it's a way of transmitting the data into the system. Now, there's internal and external. So the internal, this is an example of an internal bus, and an external bus would be like a USB cable would be an external bus, or a parallel cable to your printer, or a network cable would be another example of connecting to a bus and importing or exporting data into that system. All right, now the CPU putting this kind of all together onto the motherboard. So when you put it all together, sometimes they refer to this as the CPU case. They don't really, they're not talking about specifically the CPU chip itself. Sometimes somebody say, well, what kind of CPU do you have? And it's sort of looking at the desktop computer. And that's what they're talking about here. So it's referring to that computer's chassis or the tower. Some of you may have a desktop computer. Most people today have a laptop or portable type of computer today, but a lot of people have opted in the past to get these desktops because you could put more computing power into them, and they didn't really need to have the portability. So what you're looking at here in the picture is the motherboard. The motherboard is sometimes referred to as the main circuit board. It is what brings it all together. So you can see over on the right-hand side here, you've got the bus slots, and then you've got your peripheral ports. There's the universal USB ports. There's an RJ45 port right here. That's where you plug in your internet. Some more USB. There is an old serial port. So this is kind of a legacy port. There's an old legacy mouse port, keyboard port. I think this is an old parallel port for the printer. And that's where you plug in your CPU. So in years ago, maybe 5 to 10 years ago, people would buy these boards. They would buy all the peripherals. They could snap it all together and build their own computer systems. Today, people don't do that as much, but you still can do that. There's still people out there that do that. Now, hard drive is another component of the computer system. Hard drives, or the classic hard drive, is a mechanical device that uses a platter or a series of platters with this little drive needle. It almost looks like the old-fashioned record players, if you've ever seen one of those. And the disc spins, and it basically turns a bit of iron oxide on the plate to either left or right, which indicates a 0 or 1. Again, back to the 0 and 1, because everything is stored as 0 and 1s on a device like this. Now, what seems to be more common, and this is what I've opted to in my last computer, is to go with an SSD drive. This is a solid state drive, and it's all done through integrated circuits and chips. So it's a lot faster because you've got moving parts here. You got an arm that actually literally has a turn back and forth. These disks have to rotate in circles to find the information. So the SSD drives are far superior, a lower power consumption, more compact, and just the way things are going. These hard drives are actually being phased out right now. You see fewer and fewer of these all the time. All right, now let's go talk about the history of computer hardware and software. So I've been in the industry for a long time, and I've seen this evolve over time. And there's been major changes. Now I haven't been around for the past 60 years, but I've been around for quite a few of these years, and they've computers just continuously get faster and cheaper. So they came up with something called Moore's Law. You might have heard of this. And Moore's was, I think it's Gordon Moore's, and he was a CEO of Intel. Those are the people that make the CPU chip. And Gordon Moore predicted that computers would double their capacity every 2 years. And it's remained fairly constant. If you drew a trending line through here, you'd see that this is actually quite true. So since 1970 till 2018, computers have been consistently doubling their performance, their storage capacity every 2 years. But we've reached the limit where computers now have come to almost like a physical barrier. They've gone so small that they can no longer put more information onto the chip with the current technology. So they're moving to a new technology altogether, which has nothing to do with classic physics. It's dealing with quantum physics. So just a quick kind of history of how this all kind of came to be is you might have heard of vacuum tubes. If you haven't, this is how it all started. These are tubes that could basically hold a 1 or a 0, and with a 1 and a 0 you could use that to help process and do basic calculations. And then it went into a transistor. So I picked this picture right here, which is a vacuum tubes on the top and transistors kind of on the bottom. So they miniaturized it a little bit. And then there was a quantum leap in the late 60s and early 70s into the integrated circuit. And this really revolutionized the world and really has been hyper accelerating mankind's knowledge is this chip right here. It really did amazing things. So what's going on now is, with this chip, it kept expanding, and we did have a long run from literally the 70s until present. Like you're looking at like 40, 50 years of this chip has been around, giving us our classic computers. But what's happening now that the textbook doesn't talk about is quantum computing. So with quantum computing, it uses the quantum physics, and it's not dealing with a 0, a bit, or a byte, I should say, a bit. It's with a qubit, and it's a quantum bit, which it increases its capacity by tens of millions. And Moore's law is like right out of the window now, where in the past we had classic computers we think running quite quickly. With quantum computers, it's so fast that it's hard to even fathom this, and we really don't even understand how fast and what this kind of impact is going to happen on mankind or humankind, because the speed, the accuracy, the storage capacity with these quantum computing is literally going to be 100 million times faster, and it's probably going to be even faster than that. This is just what they've currently developed. So this is what the new quantum computer looks like. If you haven't seen this, I would encourage you to take a look at. There's a great LinkedIn course. I watched. I couldn't. I had to watch this. It was so fascinating on what's coming up into the future. And I think it's really important for anybody going to school, starting a career, to understand what kind of impact this is going to have on our lives. And it's going to be huge. So with classic computing, and I think for the rest of this course we'll be talking about that, because quantum computing isn't right out there yet, so we can't really talk about it in any real detail. But I would encourage you to have a look at that LinkedIn Learning on quantum computing to get an idea, and they do a very good job of explaining it in a very simplistic way. All right, so speeds of the computer are measured and have increased over time as well. How fast can the central processing unit actually do some kind of process, kind of logical calculation, some sort of ALU calculation? So in the early days, they were measured in 1/1000th of a second or millisecond. And I think there's a quiz question or a couple of quiz questions on this, just so you know what's a millisecond. It's 1/1000th of a second, or what's a microsecond, 1/1,000,000th of a second, or a nanosecond, which is a billionth of a second, and finally picosecond, which is 1/1,000,000th of a second. So 1/1,000,000th of a second to process some kind of calculation in the ALU. is what they're talking about here. So that's what they use. It's like if you're driving a car, you talk about it in kilometers per hour. With computers, we're talking about it in either milliseconds all the way up to picoseconds. Accuracy is of course critical. I mean, it goes back to the GEGO rule. So if there's a slight variation in the accuracy, well, it could throw things off drastically. They put up an analogy, I think, in the book that if it's off just a small critical amount in calculations, when they're doing something, they give the analogy here that the space shuttle landing on, coming back from space, wouldn't hit its target. It might end up in another country. Storage and retrieval. Now, storage and retrieval is what I was talking about back with the hard drive and the SSD drive. So storage is done locally on one of these two devices. Some of you might have a USB drive, which is kind of like an SSD drive. It's a solid state drive. And they're also, SSD drives are quite quick, where USB, because they're serial, they're reading information one at a time, it's a lot slower to transfer the information onto a USB drive. But a SSD drive, it has a parallel bus, so there's a lot more faster data transfer than it would with a USB drive, for example. All right, now I want to talk about this American Standard Code for Information Interchange called ASCII. And it's important because everything that you do as a human with a computer, you're entering it in through a keyboard or some language, whether it's English or whatever language that you're typing it out in, needs to be typed it in. It needs to read that data. So ASCII, or when computers originally started, they needed to be able to associate a symbol like the letter A with a number that could be translated into binary. So that's really an important concept, and I can kind of give you an example how you can actually take a look at doing this. So when computers are taking all the code and you're writing all that code, it's being typed in as just regular text files, then the computer can then interpret that and develop an application. When you're transferring data over the internet, you're going to be transferring a lot of the data as text, and the text is transferred in an ASCII agreed upon code. It's this American code, standard code for information interchange. Now, the reason they called it American in the beginning because they're the ones that actually invented it, and they came up with the standard. Now, the rest of the world and all the other countries of the world have come up with their languages and have added to the ASCII. It originally started off with just an 8-bit block of zeros and ones. So what they do is they take 8 bits and they put them together, and it makes technically what they call a byte. And there was 128 of these, what they call characters. Now you can think of every character on your keyboard. So the letter A would be one, the letter B would be one, and so on. The number 1, the $sign, all that kind of stuff. So if you want to take a look at how that would work, there's a great website out there here called in Wikipedia called the List of the Unicode Characters. And it's gone from 128 characters to 143,859 characters. And basically everybody in the world now or most people in the world have chimed in to add characters to this new universal code system. And back in the day, in the early days, when the American Standard Code for Information Interchange came out, they started off with the very first character, which was what they referred to as a null character or no character. And then they had what they call a start of the header, which is for printing. And then you recognize this one here, the backspace key. So they assigned the backspace key. It was assigned to a decimal value of 8. And then that 8 would get transferred into a binary number. Now, I'm not going to go through and show you how to calculate binary from a decimal. You can look that up if you're interested later. All right, now there's the horizontal tab, and then the line feed that would drop the character on a printout. So you can see in the early days, this was a very, very basic type of input that needed to be stored so that the central processing unit could actually calculate it. Now it goes up to 31 here, and then it jumps to 127. Now that's because of the way that they've displayed this particular list. But if you go down a little further, there's 32. So 32 is actually the space bar. Now, kind of fun fact, if you guys opened up, let's say, a word processor or virtually any system that you want. So for example, if I wanted to hit the space bar, I hit the space bar, it moves me in. Or if I want, I can use 32. The decimal number 32 translated into a character. Now to do that, you use the Alt key. And then you hold the Alt key down plus 32. So let me demonstrate. If I hold the Alt key down, now you can't see me, but I'm holding the Alt key down. As I'm holding it down, I press 32 and I let it go, and it just moves it over one. You can see it moved it over one character. I could go Alt. And so you're thinking, well, that's kind of an odd thing to do, which it is. But I'm just giving an example. Let's say you want the letter Q. Now, instead of typing the letter Q, I know letter Q is 81. It's the 80. So I hold the Alt key down, I push 81, and I get the letter Q. Now, this works now for 143,000 different characters. So I've got one here, a character that they've added, and you can see it's been added late because they're off into the hundreds of thousands of characters now. And it's this number right here. So if I just double click this, and I think if I hold the Alt and the X, and then I type in, oh no, what do I want? I want to just type the number, sorry. I hold the Alt key down, I type 128514, and I let go. It gives me an emoji. So you have access literally to 140 plus thousand characters, or virtually every character that's in every language on the planet, in every software program that you use as input into the processor. Now, we don't really think about it because we always use the keyboard. If you wanted a happy face, you might just use, an emoji like this. I mean, just the colon and then a bracket would be that particular emoji. And there's very limited with the keyboard, of course, but with these Unicodes, you can access everything you want. Now, if you just go in there and type in 13100 and let go, you get some kind of a I'm not sure what language that is, but I'd have to go look it up and correlate it with the number that I typed in. But there's literally tens of thousands. And if you go to the site, you can go down here and you can find any character here, and you can associate it with this right here. Now, I said a decimal number, but now they're using what they call a hexadecimal number, which is by using A through F. But let me just go down and let's say we find a symbol like this one here. You might recognize this as the yen, Japanese yen. So it's 00A5. Now let's say I want that character and I want it in my word processor. All right. So if I want that and I want to put in, I hold the Alt key down and the X key, and I type in 00A5. No, that didn't work. So what I'm going to need to do is, I think I don't do it this way this often, so I'm going to have to try another method. Oh, there it is. There's the code and there's the decimal. It's 0165. See? Okay, so I'm going to go back to my word and go Alt 0165, and there, sure enough, is the same symbol in my Word document. So you guys have access now for inputting any symbol of any language anywhere on the planet. So you can see here there's some French symbols and Greek symbols, and these actually are in order of which country joined the universal, the Unicode table. And that's why these emojicons are way down at the bottom, because they added emojis just in the last 10 years or less. So you can get an idea from there. All right, so that's pretty much all I want to go for this video because it's getting a little bit long, and I will carry this on in the next video.